Hi folks, I'm sorry it's been so long since I posted last. These are of course crazy times, but that's no reason we can't learn a little bit of Houdini. So I wanted to get back into things with a relatively simple little project here, but I think it's an interesting workflow. It's something that lets you have sort of different types of fluid interact, and as opposed to just setting their individual properties, having them actually come together and create some new fluid that has sort of its own properties. And I'll talk a little bit more about what I mean by that, but basically we're looking at kind of binary fluid reactions. So we have fluid type A, fluid type B, and where they meet, we create some new fluid type and give it some different properties. And this can let us have all sorts of different effects, all sorts of different reactions. What I'm going to focus on today is kind of this droplet-like interaction where we have a dissolving particle that will release a whole bunch of bubbles. So let's just get right into it. I'm going to drop a geometry node here, and I'm just going to call this my, let's call it flip reactions. And the first thing I want to do is just sort of show you a little bit about what I mean and basically show you pretty much everything we're going to do. The rest of it will just be flip setting up. I just want to give you a sense of the approach we're going to take here. So I'm just going to lay out a grid. That's much larger than I need. Let's just give ourselves a little grid to look at here. I'm going to scatter a bunch of points on here. Let's say, I don't know, 10,000. What does that look like? That's not bad. Oh, let's even go higher. It doesn't really matter. Sure. Nice dense grid. I'm going to put some noise on here, and I'm going to use this to drive partitioning this into sort of two different types of fluid. And again, this is just for showing what we're going to be doing. So I'm going to make an attribute. I'll just call it noise. I want this to be one-dimensional, and I want it in the range 0 to 1. We can go ahead and visualize that. Dial in the element size a little bit to get something we like. I want this a lot smoother for right now. That's probably okay. Maybe something like that. And then all I'm going to do here is drop down an attribute wrangle, and I'm going to say if this noise value is less than 0.5, I'm going to set something I'm going to call val A to 1, and otherwise we'll call this val B. So if I turn off this visualizer now, and I just say color one of these, so let's just say val A is greater than 0, we'll color these ones. By default it'll set everything to white, so let's just pick some other color. And we have to specify that this is a point group. And so there you go. We're basically just partitioning this into two different sets. I'm going to scale this again a little bit, maybe something like, oh, I don't know, this is fine. This really doesn't matter. So this is our setup, and once we get into flip, we're going to have something very much like this. We're going to have individual particles that are either part of one fluid, our val A fluid, or part of another, our val B fluid. And what we want to do is identify those regions where they're next to each other. We want to figure out which particles are in an area where it's a boundary between val A and val B. And there's a variety of different ways you can do this. I'm going to do it in a relatively, I think, straightforward way. And the basic idea is first I'm going to blur these two values. So I'm going to blur using attrib blur both val A and val B. And I'm just going to make sure this gets nice and blurred, so I'll set the step size up, the blurring iterations up. And then of course, if we were to do this initially, it won't change anything. So if we just look at this color, and by default, attrib blur is going to be by connectivity, and none of these points are connected to each other. And if we're doing a flip sim, again, we won't have any connectivity, but we will have proximity, so we can use that. And for the radius here, you can see this is very large. Once we're in the sim, we're going to drive this by p-scale. These particles don't have a p-scale. We have 40,000 within a 1 by 1 square, so we could work that out, but I'm not really going to bother. Let's just dial this down a little bit lower. And here it's not really making much difference. But the overall idea now is that we are sort of, and actually if I make this a ramp, we'll see this even better. Let's just ramp by val A, and you can see that we're blurring out this edge. So here it was a nice sharp edge, and we're just blurring it. And we're doing the same thing for val B. It's also blurring out. And the idea here then is that where, let's see if I can show this more easily. Yeah. let's just ramp these into two different colors. So we can say at CD, it's just going to be 0, 0, 0. And then we'll say our red channel will be val A, and our blue channel will be val B. So now again, here we just have red and blue. After the blur, we have red and blue where they're not near anything. So all of these blue particles stay blue because they're not near enough to any of the red ones to get any of that blurring. Same with the red ones on the inside. But in this middle ground, we get this sort of magenta color. We get this overlap. And this is what we want to target. So we basically want to find points where now val A and val B are closer together. And what do we mean by closer together? We really just mean that the difference is smaller. So what I'm actually going to do is going to jump in here, and I'm just going to say, basically what we want is to take our maximum of val A and val B and subtract our minimum. And we can call this something like delta. So if we visualize this, and what have we got going on here? I turned off the visualizer. Now you can see we get these nice little bands here. So yeah, this is our general idea here. And this is basically what we're going to use to drive our flip sim. And what we're going to do is basically just say, if this is bigger than a certain amount, so if delta is, let's say, or I should say smaller, if it's less than, I don't know, let's set an arbitrary value here, let's say 0.3, then we can say these particles we're going to convert. And if we were to just sort of color based on that value, convert greater than 0, we're not going to ramp, we're just going to make it constant. Turn off our visualizer again. Now you can see we're just isolating this band. And so what we're going to do in the flip sim is we're going to have these two fluids, our val A and val B, interacting, but we're going to convert them into a new type of fluid only at the boundaries between those two types. So hopefully that makes sense. We'll be coming back through all of this in the flip sim itself, but I just wanted to kind of show the general idea of what we'll be up to here. So I'll just call this our demo. So let's go ahead and set ourselves up for flip. So what I want to do here is set up basically a box, so basically a container of fluid, and we're going to drop a little droplet into there, and where it sort of falls through, it's going to fizz and turn into bubbles. That's kind of the idea we're looking for. So I'm going to start with a box. 1 by 1 by 1 is just fine. I'm going to just raise it up so it's sitting kind of on the ground here. There we go. So we'll move it up by half of its height. So that'll be our base box. We're going to get some points from volume. These will be our initial particles. I'm not going to worry about the point separation because we're going to drive that from inside the flip simulation, so I'll just leave that here as it is for now. And then we're going to want to set some attributes. First I'm going to set this same kind of thing. I'm going to say val A equals 1. I'm going to give this a color so we can visualize it. Our base box, let's just keep that, I don't know, like a dark red or something. We're not going to use this really at any point in rendering or anywhere else. This is just so we can keep track of the differences. And then we're probably going to want to set some properties here. So we can set things like density. So I'm going to go with something like 10. And I'm going to set a viscosity in here as well. Let's say 0.1 should do nicely. So this will be our basic container, and then we want to drop a little droplet into there. So we're going to want a sphere for our droplet. That's obviously going to be way too large. Let's just bring this down, something like, I don't know, that's looking pretty good in there. I'm going to bring that up, maybe there-ish. That's looking pretty all right. And I want to turn this into polygons, even though I'm going to scatter points into it, and I'll show you why. If you do points from volume from a basic sphere, I mean, these points are much too small, so let's really pack them in there. I'm I'm just going to go to a null because it's showing us that outer part, and I don't want to see that. You can't necessarily see it too clearly here. If I were to, I'm going way down the rabbit hole here, but that's all right. If we were to surface this, and same general property, you can see it gets sort of, it's a little bit faceted. And basically what's happening is that points from volume, it doesn't really recognize this as being a perfect sphere or anything. It's going to turn this into polygons first. So the very first thing this is going to do, and I think if we dive inside, we can probably find that somewhere in here. It might even be this triangulate. This is a mess in here. This thing has not been organized terribly well, so let's not worry about that. But the first thing it's going to do is turn this into polygons. And it chooses a relatively low resolution version of that. So if we do this ourselves, we can set this nice and high. We can give it a really nice, clean, round polygon shape. And that's going to get rid of any sort of faceting it was going to do. We're still getting these sort of flat edges, but in general, I prefer to start from polygons on the sphere because I find it gives you a better sort of round result here. Now, the other reason we want to start from polygons is because maybe we don't want this perfect sphere. Maybe we actually want to give this a little bit of noise. That'll make the simulation itself a bit more interesting. So I'm just going to drop a mountain here. And this is all much too much. Maybe just a little bit of interest in here. Again, I'm going to take the roughness down. I really just want to give this a bit of distortion. So even that's probably more than I want. So there's a normal sphere. We'll just bulge that out. There. Just a little bit of noise. Just something to shake things up a bit. So again, we'll turn this into points. Obviously, we're not going to get very many points if we use that same particle separation as over here, but we are going to fix that soon. So this is our droplet source. So we're just going to go in here and we're going to give it a different value. So this is going to be val b. And then we also want to look at its properties. I'm going to give it a color. We'll just make that black. So there's those particles. Again, we're going to have more in a second. And the last thing I want to do is if I want this droplet to sort of sink through this other fluid, then the density should be a bit higher. So let's just call this 15. So I'm going to merge these. I'll grab both of them. I'm going to Alt and drag. That'll give me a merge node. And then drop down to this null. And I'll call this our flip source. So here's all our particles. This is basically all we need to go into the flip simulation itself. So let's just go ahead and drop down a network. I'll call this flip sim, and we'll dive inside. And we really don't need very much here. We're going to want some gravity. We're of course going to want a flip solver, and we're going to want a flip object. Wire these all together. And the first thing I want to do is change my initial data here to a particle field. And I'm going to go ahead and grab that flip source we just made. So that'll bring that in. I'm going to go to my guides, to my particles, and of course turn it from sprites to particles. And finally, I don't care about the speed visualization. I don't actually want to see that, so I'm just going to go to none here, and that'll give me those color values we set outside. Last thing I want to do, this particle separation is way too high, but first we need to actually tie it to where we generated those particles. So I'm going to copy this parameter, and I'm going to go back to these, and I'm going to paste relative references, and paste relative references. So now we can go in here and we can tune this a little bit. Let's say 0.02. That's looking pretty good. We can probably even go a little bit lower, maybe 1.6. If we do this, then we're getting about 250,000 points. So that's pretty good. That should be fast enough for now. Maybe I'll even... No, I do want enough resolution that we can actually see some things here. So that should be good for now. Next, I want to deal with these volume limits, because right now if we were to simulate this, it's all just going to fall. So we want to give it a container. So I'm going to go to my volume tab here, and I'm going to go to my volume limits. And I know that this box is 1 by 1 by 1, so let's just make it 1 by 1 on these axes. And we don't need much space, but I do want it to be a little bit taller than that box, just so we have room for some splashing and some sort of jostling at the top. So I think about 3 high and 1 by 1 should be a good little container there. So this will be our volume. I'm going to turn off the visualization because we don't need that. But I do want to go back to this flip object and make sure we're closing these boundaries, because again, if I were to run this now, it's just going to fall through that floor, and now all our stuff is gone. So we want to close these boundaries. If we do that, then we get the beginning of our sim. But of course, we're not quite there yet, even for our initial setup. Of course, we have no reactions going on here. But if you watch these dynamics, and if you've done much sort of flip simulating before, you'll realize 2 things. One, it doesn't look like our different densities really had any effect at all. This droplet just sort of fell and they all merged together and splashed and jostled around. 2, this doesn't look like it has much of any viscosity going on. And both of those things are true because we need to do a little bit of extra setup. So again, on our flip solver, under our sort of volume information, first we want to go to viscosity and we want to enable it. If we don't do that, it's never going to use viscosity. And we also want to check viscosity by attribute. Now, right now, both of our sources have the same viscosity, 0.1 and 0.1. Once we add our reaction fluid, we might want to change the viscosity for that one. So we do want to make sure this is by attribute here. And then for density, density is of course always enabled because it's mass, it's got mass, it is a material, so it's going to have density no matter what. But by default, it's just taking a single value, and that value is coming from over here on the physical tab. There's our default density. So what we want to do instead is density by attribute. And so this is going to pull our density from this attribute here. So once we've enabled those 2 things, now it should behave a little bit better. We should see it dropping. And now you can see we don't get it all merging together. Instead, this more dense fluid is actually pushing away the less dense fluid. And then we're going to get this little bit of a kickback here. Now this is fine, and if it's what you want, then that's what you want. But I actually don't really want this splash, especially since what we're going to do is we're going to generate where it interacts, where it has these boundaries, we're going to generate a fluid that's even less dense, something sort of like bubbles. We're going to get this huge tail of a splash coming up here, and I don't necessarily want that right now. So what I'm going to do instead is I'm actually going to start this droplet inside this fluid here. So let's just go and set that up. And so what we're going to do is just a slight variation on what we've got here. We're going to generate our initial box here, and we're going to again have this mountain sphere, but instead of having it up here, we're going to move it down inside this fluid. I should get that box visible. So we're going to have it somewhere down in here. In fact, maybe let's see this, just so our mountain, and we'll just start it somewhere near the top, but inside this box. Now, we don't want to just generate these points all throughout here, and it would work fine from sort of the fluid simulation perspective, but in terms of what we're going to do here, basically everything is going to be adjacent to other stuff. It's all going to blur together. So what we want to do is not overlap these 2 things, but basically find those points from this box here that are inside this area and call those the other type. So we'll just delete this stuff. And what I'm going to do instead is I'm going to take this mountain sphere. I'm going to do a VDB from polygons, and this will give us a surface density function. This doesn't have quite enough resolution for me. I'm going to pull it just way down. We only have to do this once, so we don't really care about any overheads here, and even that is very cheap. So this gives us a nice little representation here. So we're just going to drop, in fact, maybe I'll just copy this one. We're going to pipe through here, and now what we'll do is basically say if our volume sample from that SDF, from that surface density function at this current position is less than 0, then we're inside that shape. Oops, deleting everything wrong here. Move all of this over. And so what this shape is, just quick reminder, this is a surface density function. So basically everywhere in this volume, it's not actually storing this surface, it's storing the distance of each voxel in this volume to this surface. So it's giving us a representation of the polygon. So positive values are going to be outside, negative values are inside. So if we sample that volume at the position of each particle that we have from here, so each of these points is going to ask, where am I in this volume? Am I getting a positive value, which means I'm outside of that shape, or a negative value? If we're getting a negative value, then we're inside that shape, and so we're going to switch ourselves to val B. And when we do that, we just want to make sure we set val A, which by default was 1, to 0. And so now we have our full box, and we're going to replace all of the points that were inside this shape with that other type. And so I want to use that for our flip source. So now if we go back to our simulation here, it's going to behave pretty similarly, but we won't get that huge splash. So again, you can sort of see through here that sort of darker particle is falling. And we should get a little bit of displacement at the surface here, just a little bit from it kind of passing through and causing that sort of kickback. But basically we're not getting that huge splash that we were seeing before, and that's what I wanted to avoid. And you can see that all of this has come down and hit the bottom here, which is what we would expect for a denser fluid. Now, believe it or not, we are basically almost done. All we need to do now is take this logic over here from this sort of demo and apply it inside of our flip solver. And that's very easy to do. We'll just sort of fully replicate it back in here. So in our flip sim, we're going to drop down a SOP solver. And we're going to just tie that right into our post solve. We don't need to set up anything crazy here. We want it to do its default normal thing. And we're going to use this default normal geometry. So it's just pulling from our flip sim. It's pulling from our flip object this geometry container. And this container just holds all of these points. So we're just going to get these particles. Yeah. So here we're getting all those particles. You can see them here. They have their val A and val B. They have their viscosity. They have their density. All of that good stuff. So the first thing we want to do is that attrib blur. And we're just going to put in those same settings as before. We're going to say val A and val B are the attributes we want to blur. I'm going to use the same values, 3 and 1 here. And I'm going to do by proximity. Now for my radius, I only really want to consider particles that are pretty nearby. And nearby, in this case, actually has a pretty clear definition. We've specified our particle separation right here. So I'm actually going to copy that value. And I'm going to paste it in here. And I'm going to say maybe within 3 times that particle separation. So give ourselves a little bit of space, but we're not going to be considering particles a long, long way away. And to make sure this thing stays relatively quick, we don't even need to think about very many neighbors. Let's just check the nearest 16. So here we're blurring these values. And if we go over and look, we'll see a bunch stay the same, but we should find, I guess we need to look basically at the middle. Oh, here we go. So you can start to see these are, we have too many particles to easily scroll through here, but you can see that they're starting to sort of blur together. And somewhere around here, somewhere near the middle, we'll get sort of closer values together. But at this point, they're sort of far apart, but we are getting this blurring. So the next thing we want to do is, again, get that sort of difference between those values. So we're going to say, we'll call this delta, and it's basically just going to be the difference between the maximum of these values and the minimum of these values. Now, you'll see I've sort of dragged this over to the side. I'm not lining it up. Obviously, you can put these things anywhere you want, but I did this for a reason, because we don't actually want to blur these values on our original particles. And the reason for that is that these are supposed to represent each particle is either type A or type B. We don't want them to be fractional types. That's not what we're trying to do here. That is one way to approach reactions between fluids. What we want to do is say you are discretely either A or B, or the new type that we're about to create. So I want to do this blurring on sort of a secondary branch, and then reference that value back into the original geometry. So we'll put another wrangle here, and we'll just pipe this in on that second input. And because we're coming straight from this list of particles, and these are all just particle operations, we're not changing the ordering anywhere here. So that means particle 1 here is going to be the same particle as particle 1 here. Everything's been processed, it's all in sequence, we haven't shuffled or rearranged anything, we haven't added or deleted particles, so we can very safely just reference these values using @ptnum. So we're going to do that. So the first thing we'll say is let's just flip these values, because delta right now, when it's close to 0, that means they're really, really on a border. When it's close to 1, that means they're not on a border. So these are actually ranging from 0 to 1 for on a border versus not on a border, and we kind of want to flip that. So what I want to do, well, let's just say, yeah, let's get a value, we'll call it convert, and we're going to reference those values. So it's going to be input 1, which is our second input. The attribute is called delta. That's what we specified here. And we can just refer to ptnum. So now we've pulled over this value, and you can see it ranges from 0 to very, very small. So there are some cases where they're really, really close together, and these ones would be sort of boundary points. So what we could do here is basically just say if convert is, oh, and I didn't flip it, so let's say 1 minus, that's what I meant to do. So now, if we look at these again, you can see usually it's 0, which means we won't convert, but there are cases where it's up at 1. And these are cases that are on the boundary. So we've just remapped this 0 to 1 range to a 1 to 0 range. So 1 means we should convert, 0 means we shouldn't. So now we can ask if convert is greater than some threshold value. Let's even just make a little channel here. Then we're going to do something. I'll make that channel, and let's say if it's greater than 0.8. We're going to dial this stuff in a little bit differently soon, but this is the basic idea. So if that's true, the first thing we might want to do is set a group. I'm going to set that as Rx, and this is just short for reaction, so we're basically saying this is our reaction group. If we're in that group, we're going to want to say we're no longer interested in val A and val B, so these are going to go straight down to 0. And we might want to set some new properties. So I want these to be like bubbles. So I want them to float up to the top. So that means I want my density to be much lower than usual. So I'll set that as something like 4. And finally, I'm going to give it a new color just so we can see it nice and easily. So I'll set that to white. Now, because we're setting these groups and we're running over this each pass, on the first pass we don't have any of this group, but on the second pass we do. So what I actually want to check is if we're in this group, we'll do some reaction-specific stuff, and we'll come back to that in a moment. Otherwise, we'll do this stuff. I'm going to save, it's going to be upset. The reason I'm doing this, you can't easily tab over a whole group in this view, but if you go to Edit String and bring up this little dedicated editor, now I can grab all of this and tab it over all at once. And that's just a little bit easier. So there we go. So basically, if we're in the reaction group, then we're going to do whatever we might want to do with it. Otherwise, we're just going to check this. So if we're not in the reaction group, we're going to check if we should be, and if we are, then we'll sort of move ourselves over. So if we apply and accept that, this is most of what we need to do. We're going to add a little bit of extra stuff just to make this more interesting in a minute, but this is basically the whole thing. So let's go here and switch this to the output. So now, and in fact, I'm just going to use a dot import here to bring in these fields. It's not strictly necessary under this circumstance because we're really just fetching this geometry and there's no other geometry in there, but it's good practice. So here's our information. You can see we have that blob in there. I'm going to maybe, just so we can take a look at this, I'm going to delete everything that is z less than 0. We'll put this on points. And let's see. Okay. So you can see it has deleted those points. This is just a viewport thing. So new scene view, there we go. So now we can see that blob inside. And if we step forward here, you can see that our reaction is happening way too quickly. So it's just sort of bursting outwards and covering everything. So that's all right, we can deal with that. First thing we might want to do is set this threshold a lot higher. Maybe even like 9.5. We can try that. Again, that's just sort of swamping pretty much everything. So maybe instead what we want to do is have a bit of an accumulation here. And so instead of just saying at each step, let's grab this delta value, let's actually accumulate this value. So we're going to say on each step we're going to add this delta, and then we're going to compare that to a much larger value. So let's say if we get up to 5. Let's head back out. And now it's still instantaneously getting this big ring here, but we are having it come in a little bit slower. So that's almost what we're looking for. And the problem that we're running into here, that's right. What I actually want to do here, I don't want to do this for every single sort of test we're doing. I basically only want to look at this expression if we have sort of a reasonable amount of overlap. And we can define a reasonable amount of overlap by saying that our minimum value should be a certain size or larger. So if we're way out in the other ranges, we don't want to even consider it. Because what's happening with our blur is pretty wide. And we want our blur to be doing a lot of work to make sure we're getting nice mixing so we can actually compare these values, but we don't want to compare them all the way inside here. We really want to restrict our consideration to this sort of range near the outside. So what we can do for that is basically say if our minimum is greater than some certain value, and let's use that 0.3 we had back out there. I'll just make a note here. 0.3 is arbitrary. So if that's the case, then our delta is going to be max minus min. Otherwise, we'll just say that it's 1. So even if it might have been much larger, we're just going to say that it's 1. So this is going to be restricting our attention to only cases where we have a fair amount of overlap, where our minimum value is at least 0.3. So this is really going to restrict our range a whole lot more. So now, hopefully, if we can get our scene view to refresh, there we go. Now we should have it come through slowly and only on the outside there. So that's what I'm looking for. I want to see these particles, this exchange happening only on the outside. And so right away you can see that this is basically working pretty much exactly like we might like. Only where we're getting that interface between the red and the black fluids, we're having it turn into these sort of white bubbling fluids, and those are getting that new density, which is much lighter, and they're drawing themselves all the way up to the top there. So there we go. Now we've got this sort of nice little effect going on here, and this is more or less all that we want and all that we need. So I'm just going to do a couple extra things, a little bit of sort of quality of life and a little bit of setting up for other effects if you want those. And in particular, one of the things we might want to know is how old are these newly reacted particles? So to do that, when we first create these new particles, we're going to store a new attribute. And I'm going to call this Rx onset. And I'm just going to set this to the current time. So now we're keeping track of when this particle was first created. Now we can use that up in this reaction specific stuff. So first what we can do is get our age, and then it'll just be the current time minus that Rx onset. And so this is going to be specified in seconds. This can be nice because if you change your frame range, this won't change. This will still behave the same. On the other hand, if you want it to be in slow motion, but you want the same relative sort of timing, then you'll have to change this to frames, or you'll have to change this relative to that. But basically right now this is going to be in terms of seconds. You could also do it in terms of frames. You could just say at Rx onset F for frame is their sort of current frame. That doesn't work in here. I guess we need to use, I think, at frame or something like that. I'm going to keep time, though. It just makes more sense to me to work in terms of seconds right now. But of course, you can do that any old way. So now that we have this age factor, let's just use that to drive something else. So for example, maybe we can drive viscosity with it. So we could say our viscosity can be fit using our age, and maybe we want to go from sort of maybe half a second up to 3 seconds. Maybe we go from our original viscosity or even a lower viscosity to start straight from 0, and maybe we ramp up to a much higher one. And so now for each of these new particles that are created, these little bubbles, they're going to start, and they're initially going to be very low viscosity. They'll flow very easily, and as they get older, as they get to about 3 seconds old, they're going to start to get sort of thicker and thicker and drag more and more. If we really wanted to shape this, we could even put a ramp on here, viscosity from age, and just use that in there. We would normally, this is going to return in the value in the range 0 to 1, so these ramps will always return in the range of 0 to 1. I actually want to go from 0 to 1 for viscosity, so that's fine. But if you didn't, then you could just drop a bit of 1 around here and map that to your min and max, whatever those might be. But in this case, 0 and 1 seem pretty good to me. Well, let's just keep this here just in case. Just in case. So here's our ramp. That's all good, and we'll just map that to 0 to 1. So this extra fit01 right now is redundant, but if I decided actually I want it to be even more viscous, or I want it to start sort of higher, we can tune that more easily now. So here's our ramp, and what we might do is basically let it go and sort of bend up near the end there. So we'll have it accelerating near the end. And I'm going to change these to, I like Camel Rom. It's just a little bit rounder. Okay. So if we do this, it should look pretty similar. But as these particles get older, they're also going to get, and we could even, let's just visualize this. Let's take our Rx group, and we can do a ramp from attribute, and we can ramp viscosity, just so we can take a look at this. And let's make this maybe like a black body color or something. This is not a good ramp for this. Let's use, that's not a great ramp either. Let's just make sort of a blue toned one. All right, good enough. Now we can just see it against these other colors that we had. So now, as this comes through, you'll see the viscosity starts very low. It flows really freely. As it gets older, you can see sort of the color range is changing, and this should also be changing that viscosity. So as these particles are getting older after their creation, they're getting more and more viscous, and they should start to sort of move a lot more sluggishly. And that's really just kind of a look tweaking, but depending on what you're trying to do, it may not be bubbles. You can do any sort of thing with this same process. You might want to sort of drive viscosity, you might want to drive divergence, you might want to drive temperature. There's all sorts of things you could drive with both age and this sort of this reaction creation. So I'm just going to do one extra thing here. Instead of cutting down the middle there, let's just pull out now it's not showing me anything. Why not? this is just val. I want val A. There we go. And I want to delete selected. There we go. So now we can just pull out that central part, and we can see what that looks like. And we're getting this nice sort of dissolving effect here, and we can see that sort of viscosity is ramping over time. So honestly, that's pretty much everything for this effect. And because this is a nice short tutorial and a simple sort of effect, I'm going to talk a little bit about how you might go about rendering this. So to do that, the first thing you would probably want, and I'm not going to bother here just because it's a pretty lightweight simulation, so we don't need to, but you would probably want to throw a file cache in here just to save out these particles. I wouldn't do a compressed fluid output necessarily because you've got sort of custom particles and things going on here. You can set that up in your compressed fluid cache, but anyway, I'll leave you to do that on your own. And then what we want to do here, the way I rendered this in the sort of demo I showed at the beginning, the idea was we had this clear fluid on the outside, and then we had this droplet falling in, and that was turning into bubbles. So we basically have three different things we want to set up here. So let's just give ourselves some little placeholders. So I'll call this our base fluid. And then over here we want to do maybe our droplet. And we'll want to do our bubbles. So for our base fluid, I actually just want to do a particle fluid surface with the whole thing in here. I want to take everything regardless of what its type is, and I want to mesh that all together. So we're going to copy that particle separation, and we're going to drop that into here. Paste relative references. If you're using anything other than Mantra, you might want to turn this to surface polygons. I use Redshift. It does not like surface polygon soups. It only likes surface polygons, so I just switched that there. And so we're just going to mesh all of this. Now, an extra little bit of cleanup. If we look at this in our smooth shaded view, it's not too bad right now, but you can see that we're getting sort of a little bit of rough edges, and especially you can see it on the bottom here. And depending on where you're at in the simulation, you might get this. You can see these pock marks along the edges. If we're thinking of this as like a glass container, this isn't super ideal. We wouldn't really see this on the edges here. We want these to be nice and crisp. And so one really easy way to do that is to just intersect this with a nice plain regular box. So I know we had something that was 1 by 1, so let's just make this some big tall box that we know is going to span everything we are interested in. I might even make this a little bit taller or a lot taller. That's just fine. And then let's just scale it a tiny bit. Just enough that we're cutting on the inside here. And now we can just do a nice Boolean intersect. So we'll take this mesh, another reason to use surface polygons instead of the soup, and we'll just cut that. These guys have different sort of normals set up, so we just want to sort of reestablish our normals here. And now we get this nice crisp set of edges with just the fluid sort of being meshed on top there. You can see we also get the bottom. We don't necessarily care about the bottom, but in case we do, let's just do our old friend. Oops, paste relative references, and just set this up right at the ground there. That's right, the scaling is going to be no good there. Let us set that back to 1, and we'll just do that here. 0.95, and we can go plus 0.05. So that'll just bring it up a little bit from the bottom as well. So there we go. So now we have a nice sort of flat-bottomed and flat-sided tank with just the fluid meshed on top here. If we look at our flat wire shaded, it's doing a pretty good job. Sometimes what you'll see, and maybe actually if we put this as a polygon mesh and give it some divisions here, sometimes you'll get some sort of ugly effects along the sides here. Sometimes you'll get really weird normals. Right now we don't have much rippling near the edge, so it's fairly regular. But if you do get any of that, you can just go into here and turn off this detriangulation, because it sometimes causes some real trouble. It can make the geometry a little bit weird. It makes it lighter weight, but it can cause troubles with normal. So if you're seeing any of that, just turn off that detriangulation. So this is our outer surface, and I would probably just render this as like clear water. Very, very simple. The next thing we want is our droplet. And so for this one, we want to isolate specifically that one set. So that was going to be val B, I believe, yes. So our droplet is val B. So we just want to isolate val B greater than 0, and we have to specify that this is points. And so that gives us just these ones here. And again, we'll do a particle fluid surface to get that. And the last thing I want to do here actually is under filtering, because I want the bubbles to be sort of sitting on the exterior of it, not necessarily embedded in it, I want to actually erode this a little bit. So by default, these things are all linked, so I'll just delete this channel. You can see it was blue. Now we can turn on erosion only. Again, delete this channel, which is normally tied to dilate. The reason for this is basically you dilate, filter, and then erode back by the same amount. This is like a classic workflow. If you look at VDB reshape SDF, open and close are doing that. You're basically dilating and then filtering and then eroding, or eroding, filtering, and then dilating. I forget which one is which, but basically by their names, one of them will tend to open up holes, the other one will tend to close them up. So that's what all this is about. That's the reason these things are by default tied together, because a normal workflow would be to dilate it, smooth it a little bit, and then erode it. But we just want to erode, and just a little bit. Just enough so their surface is kind of pulled back from where the bubbles will be. And at this resolution, this is pretty ugly, and that's really because we're doing kind of a low-res sim here. We don't have a whole lot of particles to work with, and we're fairly late where it's getting dissolved. If we move back to here, it's not quite so bad. So your mileage may vary. You may not want to keep this, especially if you have a relatively low-res sim. You might want to just keep sort of this level, but I like to have this in here as that. An alternative, if you don't have many particles, you can go back and change your droplet scale. So if I change that to 0.8, we also get this sort of insetting, but instead of insetting by a whole sort of voxel, we're just insetting by a little bit of an offset. And what we're basically saying is our individual droplets are smaller than they actually are. So just because we're working with a low-res simulation here, maybe I'll do that here instead. So let's call this 0.8, and that'll pull that back. So this was our base fluid. Now this will be our droplet. And the last thing we want are our bubbles here. And so for our bubbles, we want to split out just those reaction particles. And fortunately, we have a group for that. So that gives us just these particles here. And then what I like to do for bubbles, and what I did in that render that we're kind of basing all of this off of, is I start them small, and then as they get older, they grow and get larger. And so this is another case where we want to use that Rx age that we defined. So to do this, I'm just going to go down here and do a couple of things to p-scale. First, I just want to set it a little bit randomized from point to point, just to give it a bit of noise so that they're not all exactly the same size. So I'll just randomize from ID, and that reminds me, I'll come back to this in a second, and maybe from 0.01 to 0.05 seems fine to me. Now, of course, the issue here, and you can see this right away, ID is just -1 everywhere because we've asked it to use ID, but ID did not actually exist. If you're doing pop simulations, ID is there by default. If you're doing flip simulations, it is not. So if we go back to our solver, to our particle motion, we want to add an ID attribute. And so now we'll get a unique ID for everything. And that's what we really wanted here. So we'll have to resim this, but that's fine. The other thing I should note, if you've seen any of my other sims, you'll note I often turn off reseeding. I didn't in this case. However, if you want to use this effect to drive, for example, divergence, you're going to want to make sure that you do turn this off. Because when you reseed, if you say, so the use case I might be thinking of here, if you're reacting fluid, if you set high divergence there so that it all pushes away, if you have reseeding, Divergence is going to push them apart. That means it's going to get less dense. That means it's going to add extra particles. It's going to interpolate those, or it's going to grab them from the nearest ones, which are going to have high divergence, and the whole thing will just explode. So just make sure you're mindful of when you're using this and when you're not. In general, when you have your own effects and your own SOP solvers in here, you really need to be mindful of how they're going to play with reseeding. In this case, it's really not a big deal. We just have two fluid types. They're going to sort of reseed. They're not going to interpolate val A and val B. They're just going to get the nearest particle. So that's all fine. So everything will actually work just fine with reseeding in this setup. So I just thought I'd mention that. But the real reason we came in here was just to make sure we add this ID attribute. So let's just run this again. And now if we look on these particles, they do in fact each have individual IDs. That means this p-scale will give them a nice sort of variable range here. So p-scale is ranging from 0.05 to 0.01. So that's perfect. So that gives us some initial noise. Now we just want to factor in our age. So this is like our base scale. Now what we want to do is multiply this by some other value. So I'm going to do my old Fido1 ramp. There we go. And call this our age scale. And we're going to fit this from our reaction age. And let's say, what did we use in here? In here we went from basically 0.5 up to 3. So 3 seconds was our sort of when we hit our maximum viscosity. So we might want something like 3 seconds for our sort of our growth here as well. So let's just fit this from 0 to 3, map that into 0 to 1, so we go into our ramp nicely. So our ramp is just going to reshape. So we're basically from time 0 to 3, we're going to use the ramp that we're going to reshape here, and that's going to return a value in 0 to 1, and then we're going to fit that into something. So we can multiply this from, let's say they'll start very small, and then they'll get up to their full size. So if we add this ramp here, and we can give it kind of a similar shape to what we saw before. I want to bring this up enough that it's really showing up initially. Something like this is looking pretty good to me. So if we were to, I guess we can just visualize this. Let's just grab our p-scale. Oh yeah, that won't work quite right because it's going to automatically fit that range. I'm just going to use a ramp. You can do this in the visualizer itself. You can sort of fit its range, but at this point it's easy enough to just now why is it, I guess on frame 1, because there are no Rx particles, it's getting confused. But if I specify points, what it's doing if I don't specify anything, it doesn't recognize this group, it doesn't see it anywhere, so it just says, I don't know what to do. If I tell it explicitly this should be a point group, it doesn't see it anywhere, so it says, okay, I guess I haven't found anything. Split can be a little bit weird. In fact, most of the nodes with the group type, they're okay at guessing, but they're not great at guessing. So it's often good to make it explicit. Yeah, so if we do a ramp from attribute on p-scale, it should go from basically 0 to 0.05. Turn this into something a bit more interesting, like infrared. So now you can see at the beginning, they start, and they're pretty much all very small. And as it goes through, they have their individual sort of variants, so we get differences in size, but we also get them sort of moving more and more towards these sort of higher values. And of course, they're not all going to get into this range because some of them have a minimum size of 0.01. If we were to narrow that range, let's say just 0.03 to 0.05, we'll see a lot more in that upper range there. But again, we're not even up to our 3 seconds yet, so if we let that keep going, now you can see we get our maximum size particles out here, and again, the new particles are still showing up very small as they get initially created. So I'm going to drop this back down, maybe to 0.02 is fine. And these are our bubbles. So now I would come back out here. This is really just my simulation. I'm not going to render that. I'll drop a new geometry for each of those other things. I'll call this base fluid. I'll call this droplet. I'll call this bubbles. And we'll just object merge into each of these. So our base fluid, we're going to grab that base fluid there. Here it is. Our droplet, we're going to grab our droplet. There's that sitting inside. And our bubbles, we'll go ahead and grab those bubbles. So now we've got pretty much everything. What am I seeing here? Yeah, so now you can see these weird normals I was talking about. I thought I fixed that. It should be not doing that. Maybe I want to get rid of these tiny seam-adjacent edges. No? Maybe my cusp is just not good enough. There we go. All right, we'll cusp a little bit more. Hide everything. Just show me this. I just want to make sure I'm not cusping my surface too much. That's not too bad. It's a fine balance. I'm going to make sure the edges are okay, but also the surface isn't getting all weird and faceted. Well, now I'm higher than I was before. Has to definitely be lower than 60 because we saw it at 60. Let's just go to like 55. Hopefully that's good enough. Okay. So here's everything all together. We've got our particles, we've got our droplet, we've got our base fluid. I'm going to render this in Redshift just to sort of show you how this would look. It'll be a little bit different in Mantra, but everything's faster in Redshift, even if it doesn't always look as nice, so I'm just going to use that. So I'm going to need a light dome. I tend to be pretty basic with my lighting. I really usually just use an environment light. So I'm going to grab a map for that. And I've got some HDRIs here. I'll just use something like this. And I don't actually want to see that in the background. And I don't want to see it in the background of the, well, I'll leave it up in the render actually. We want to see this kind of from the front here. So I'll just set up something like this and make a camera, control click to get a camera there. I'm going to lock it and switch to this mode so I can kind of zoom into something nice. And I'm going to change this camera to be something like a nice Instagram format. We all love that. All right, there we go. Good enough. So we've got a light, we've got a camera. Now we need some materials. I'm gonna go to the shop network. Make 3 materials. We'll call this bubbles, droplet, and base. And we're gonna use some real simple materials here. Again, you could do something very similar with Mantra. So really I'm just gonna use a straight water shader for this. Not gonna do anything extra there. Another material, oops. Another material here. For the droplet, I'm gonna use a tinted glass shader. I'm gonna set my ROR to the same as water. And I want it to be bluish. I want a nice blue droplet. That's going to be too dark. Something like that is probably fine. We'll play with the absorption scale in a second. And for my bubbles, I don't need anything too fancy. I'm going to call this water to begin with. But I'm going to tweak my IOR to be basically like going through air practically. So just very, very small. And I'm going to call this thin-walled. And that should be good for that. So if I go back to here, my base fluid, I want to give that base material. My droplet, I'm going to give that droplet material. And my bubbles, I'm going to give the bubble material. And I'm going to make sure that this is rendered as particles. So let's see what that looks like. And there we go. That's coming along a little bit. That background is much too bright for me. Let's just pull that down. That's looking a lot better. Pull it down even farther. There we go. These bubbles are probably a little bit too big here for me, so let's just scale them here. That's looking okay. We're getting something weird in the reflection on the bottom, I think. What am I seeing there? These bubbles are a little bit weird. Right. Yeah. I forgot about this. So when we clipped the bottom of this thing back in here, this box, we kind of clipped the bottom of this whole thing, and that meant that our droplet can actually extend past there, whereas it won't extend past the bottom of this. So let's just see if we can finesse this just enough to get a flatter bottom. Honestly, even at 0, it might be too much. And this is really just tweaking. I just want to make sure that, yeah, that should be okay. I want to make sure that this droplet is entirely inside of this mesh. So that should fix whatever we were seeing there. Okay, the reflections are still weird. I think this is going to be a reflection-refraction limit on the renderer. Again, there's a whole lot of tweaking that would need to be done in all of this. The reflections and everything are very strange here. It might even help if we just took off that background. Now we just get the reflections. I don't want to get too deep into this, but this is basically the setup that I used. You would probably want to put maybe a grid back here to get this to look proper. Our XY plane. I'm going to unlock that, go back. Now our grid is kind of cutting through. Push that back there maybe. Now we can't see our poor bubbles at all. So this is all going to be a matter of sort of tweaking until you get something that that you like. I can make this a little bit darker. Now we start to see that stuff coming in a little bit more. And you can start to get the sense of how you would set this up. But I don't want to spend this whole time sort of reconstructing these shaders. But you can see how it's pretty easy to set up these nice little variable bubbles here. You can start to see them. They're all sort of moving upwards. And at the top, which we've cut off here, I'm no longer locked in my camera. We get this nice sort of surface interaction as well. We get all these bubbles kind of foaming together. So that's really all I wanted to show today. As I say, it's a pretty simple setup, but you can do a whole lot with this. So making bubbles is not kind of the only thing that you can do. When you're sort of setting things up, you can tweak any of these different properties: density, viscosity, divergence, temperature, any of your own custom attributes you might be using across these two fluids. And of course, when you create your third fluid, you can set it to do whatever you like. So here I did something very simple rather. I only changed density, and then we ramped viscosity a little bit over age. But again, you can set any new properties here. You can set anything you like across age as well. So if you want it to change and then revert back, you could do that very easily. You could even say, you know, if age is greater than some value, maybe once it's 10 seconds old, you might say, now I'm not in this group anymore and go back to one of the other values. So you can do all sorts of things in here. This is really just a skeleton framework that I think hopefully provides something useful. Finding these little boundaries and reacting based on them is really a very simple step, but it gives you a whole lot of power to do some interesting, some fun custom things here. As always, thank you very much for watching. I hope to have more of these things coming out soon. It's been sort of a whirlwind of the past few months. I had a move internationally in the middle of a pandemic, changed my career. All sorts of stuff has been changing, so I'm sorry I haven't posted recently, but I'm hoping to get back on top of things, and I thought I'd start us off with something nice and simple. So if you enjoyed this, please do let me know. If you use it for anything, I would love to see it. And as always, if you've got any questions or concerns or comments or requests, please do leave them below. And if you're not subscribed, please do consider doing that. Thank you very much, and goodbye.